In this lesson, we're going to review some more quadratics. So we're going to review completing the square to change an equation from standard form of a quadratic into vertex form. And we're also going to look at a specific application of quadratics to do with profit and revenue and cost, and see how we can use quadratics to help us solve problems involving optimizing money. So let's start with completing the square review. Recall that standard form is y equals ax squared plus bx plus c, and vertex form is y equals a times x minus h squared plus k. These are both forms you should be pretty familiar with at this point. And what we know is that vertex form has a lot of benefits. We can use it for graphing easily. We can get the vertex easily. We can see what the domain and range are from that, whereas standard form isn't necessarily as helpful because we don't immediately see the vertex. So completing the square is a process that changes a quadratic from standard form to vertex form by creating a perfect square. Remember what a perfect square is. A perfect square in terms of factors would be something that's, say, got the same two factors. So perfect square as far as numbers go would be a number like 4 or 9. 2 times 2 is 4. 3 times 3 is 9. So something we could take the square root of. So if I had a quadratic that had two identical factors, that would be a perfect square because that would be the same as x plus 2 squared, right? X plus 2 squared, the way I wrote it out front, literally means x plus 2 times x plus 2. The squared is on the bracket. It means I multiply the whole bracket by itself. If I expand that out into standard form, I'd get x squared plus 4x plus 4 in this case, just doing FOIL on that. So this is what's called a perfect square trinomial. So I want to have a perfect square trinomial so that I can then write it in factored form. Think about it. Vertex form has got this perfect square sort of buried in the middle of it, just like we can see x plus 2 squared is a perfect square, while x minus h squared is a perfect square. You know, depending on what value I put in for h, it'll be different perfect squares, but it's that same format. Then we've got this a and k that are going to be tacked on to make it fit exactly what the situation is, but we're going to try and change things from standard form into something that's got a perfect square. So here's the basic steps, and I'll go through them, and you really want to be good at completing the square. You want to be fast at it, so I'll go through it, follow along, and if necessary, stop this video and go back and watch it again. Watch it however many times you need to until it really makes a lot of sense to you. So the first thing I want to do is I want to create a perfect square just out of the first two terms. So that plus 5 on the end, obviously I have to keep it. It can't go away because then I'd be changing the equation, but I'm going to sort of ignore it. I'm not going to work with it anyway until later. So I'm going to take this x squared minus 14x, and I'm going to try to create a perfect square out of that. So a perfect square consists of obviously two factors that are the same. And in order for that or when that happens, that means that my last number in my trinomial, if I was to expand it out, will always be a perfect square because it'll be 2 times 2 or 4 times 4, which would be 16, or 3 times 3 is 9. And my first number is always a perfect square as well, or my variable, x squared, is also a perfect square. I could take the square root of that would just be x. So I put brackets around this. So you want to start by putting brackets around your first two terms. And you're going to create your perfect square within that. I'm going to introduce a third term inside the brackets that's going to make this be a perfect square. And the way I'm going to do is I'm going to take half of this number here and square it. So half of 14, negative 14 in this case, but it doesn't matter. When I square it, it'll become positive. I'm going to take half of 14 and square that. So I'd get x squared minus 14x. So I'm just copying that down again. But I'm going to take half of 14 and square it. So 7 is half of 14. And when I square that, I get 49. So I'm going to add 49 inside the brackets. But as you know, I can't just add numbers willy-nilly inside an equation because then it changes the value of the equation. So I'm going to also subtract 49 at the same time. And then I'm going to put my end bracket, and then I'm going to put the plus 5 down. I'm just carrying that plus 5 along for now. Now, it may seem odd to add 49 just so I can subtract it again, but that's okay. You're going to see that we're going to do different things with the two different 49s. This first 49 here is my perfect square that completes the perfect square inside the brackets. In fact, this whole part I've created in yellow, that I've colored in yellow, is a perfect square trinomial, which when I factor it will give me two identical factors. This other negative 49 is sort of like a byproduct. It's a leftover that I don't really need. And I want to get it out of the brackets. So I'll do that. I'll take it out. So I'll have x squared minus 14x plus 49. And I'm going to take that 49 out, and I'll have minus 49 still plus 5. Okay, so inside the brackets, perfect square. Outside the brackets, just sort of the leftover junk. So I could even simplify what's outside the brackets for now if we want to really take this slow. So negative 49 plus 5 gives negative 44. So I can just collect those together. These are like terms, aren't they? They can just be collected. As for my perfect square inside the brackets, let's factor that. So I want two numbers that multiply to give 49 and add to give negative 14, calling our factoring from before. Well, it's going to be the same number twice because that's how perfect squares work. In other words, if I had negative 7 plus negative 7, I'd get negative 14. And if I had negative 7 times negative 7, I'd get my 49. So if I factor it, I get two identical factors. But when I have two identical factors, I can write it as a single factor with a squared on it, as I just did there. Once I've done that factoring, then you can see that it's now in vertex form. It's done. I can tell the vertex is 7, negative 44. The a value is the same as the a value when it was in standard form. It's positive 1, but that doesn't really matter. So that's a really basic completing the square. Those are the steps. Sometimes there's a little bit more to it, though. So if we have what we all call an a value in front of the x squared, that has to be dealt with. So the first step, I'm still going to start by putting brackets around the first two terms, but the first step, rather than doing what I did above where I just took this half and squared it, I need to common factor out that a value. So that a value, that 2 in front of the x squared, needs to come out of just the first two brackets, two terms, the two terms inside the brackets. So 2x squared divided by 2 is x squared, and this 20x divided by 2 becomes 10x. And I still have 41 on the end, because this 41 is not inside the brackets, so it doesn't get common factored out. So this is what I'm going to try to create my perfect square out of now. So that just like the 41 is going to stay at the end, now the 2 is going to stay out front, but I'm only going to focus on what's inside the brackets. So I'll take half of the 10, which is 5, and I'll square it. 5 squared is 25. I'll add 25 and I'll subtract 25 like I did in the previous example. Again, this is my perfect square. The minus 25 is leftover stuff that I want to get rid of. I want to take it outside of the brackets and just get rid of it. There's one extra thing I have to be worried about in this case, though. This 2 out front, when I take this 25 out of the brackets, it's not really a minus 25 because that 2 out front is multiplying against each term in the brackets. So really that minus 25, it has a value of 50, negative 50, because 2 times negative 25 is negative 50. I need to actually do the multiplication if I take that 25 outside the brackets. So I'm just going to rewrite it with the 25 outside the brackets, the minus 25 outside the brackets, but it's becoming a negative 50 because I multiplied it by that 2. So I'm going to multiply it as I take it out. And I still have the plus 41 there. Otherwise, everything goes on as before. Keep the 2 out front. Tidy up what comes after the brackets. And again, I'm just showing my work, but I'm just going to leave the perfect square as it is. But negative 50 plus 41 is negative 9. And then when I factor this perfect square, I want two things that are going to multiply to give 10. Sorry, multiply to give 5. Third time is the charm. Multiply to give 25 and add to give 10, which would be x plus 5 times x plus 5, which I would rewrite as 2 times x plus 5 squared, because x plus 5 and x plus 5 can be written as x plus 5 squared. And now we've got it in vertex form. So this example was meant to show us what we're dealing with for if there's a number in front of the a squared. All right. The same process applies even when perfect squares include fractions or decimals. So we don't have to have numbers that work out nicely. They have to be, we can just do the same steps no matter what. So let's just go through it and see how this one works. We've got x squared and plus 5x. We're going to make the perfect square out of that as best we can. And the 7 stays on the end. So I'm going to take half of 5. Half of 5 is 2.5, right? I'm going to write it out like this, 2.5, and I'm going to square that because that's where I make my perfect square. So half of 5 is 2.5. I'm going to add 2.5 squared. I'll actually square it in a moment. But I'm also going to subtract that 2.5 squared again because we add and subtract the same thing. And when I square 2.5, I get 6.25. So this is going to be my perfect square again. And I'm going to have to subtract 6.25. And again, I don't want the 6.25. I want to take that outside the brackets. And I'm just going to tidy up those numbers at the end. And so I end up with 0.75 outside the brackets. But this is my perfect square. So I need two numbers that multiply to give 6.25 and add to give 5. That might be a little harder to think of because we don't generally factor decimals, do we? But it turns out that since we're always going to have the same numbers inside the brackets, there's a shortcut we can take to know what the number needs to be. It's always going to be half of this middle number. So in other words, looking up here, we had a minus 14, and we took half of that, and we had minus 7 and minus 7, right? Here we had 10. I took half of that, and I got plus 5 and plus 5. So it's always half of what is inside that x, the brackets with that x term. Half of 5 in this case is 2.5. So it would be x plus 2.5 times x plus 2.5, which can be written as x plus 2.5 squared, and then I have the 0.75 on the end, and that's vertex form. So the exact same thing works whatever format you're in, whether it's decimal or not. And here's another one, just so we can have lots of examples. Again, this is one that's going to have decimals and numbers in front, so steps are the same. Let's see if we can do this kind of quick. We're going to take the 3 out as a common factor. Even if it isn't really a common factor, I'm just going to divide each term by 3. So I got 5/3 x plus 2. I could do it as a decimal. If I do 5 divided by 3, I get 1.6 repeating. Maybe I will do that, actually. It'd be a bit easier, I guess, to work with. So x squared plus 1.67, I'll round it a little bit. So I took that 3 out. I didn't want to have anything in front of the x squared. And then I'm going to take half of that 1.67 and square that. And what I get when I do that is, let's see, is 0.69. Is that right? Yes, I guess it is. Let me just double check. 1.67 divided by 2 squared 0.6, well, 0.7. So plus 0.7. And of course I have to subtract that again, 0.7. And again, this is my perfect square, believe it or not. And so then I have 3 times x squared plus 1.67x plus 0.7. And again, this is what I want to take out. So I'm going to take that out. But remember, there's a 3 in front this time, so I have to multiply it by 3 before I take it out. And so that's going to be 2.1. So I'm going to take out minus 2.1 plus 2. And again, I'm going to take half of this term, which was the 0.84, let's say. So x plus 0.84. That's going to be all squared. That's I took a shortcut. I didn't write it out twice this time. I just did it once with the squared. Hopefully that didn't confuse you. And then negative 2.1 plus 2 equals 0.1. And there it is in vertex form. So those are 4 examples of completing the square. And again, if you're not clear on them, give the practice questions a try. But if you're not clear on them, make sure that you go back and look at my steps again. Now, there's one other thing that we're going to do in this lesson. It's pre-filled in. It uses completing the square, but it's related to it. So a couple more terms. So there's something called a demand function. So, sorry, let me just set the stage here. We're dealing with revenue and a particular application of quadratics. When we have quadratics, there's certain things that we can model with them, such as things like balls being thrown up in the air. That's a common one. But money, too. So if you had a business, say you had a business and you were selling a product, maybe you had the price of the product here, and then the revenue here. Then as you increase the price of your product, going along the x-axis, if you increase the price of your product, then it makes sense you're going to get more revenue for the products that you sell. But eventually, your price might get so high that people stop buying it. So then the sales are going to fall off, and you're going to start getting less revenue until you've priced your product too high. So that's one of the types of applications we can do with quadratics, and that's what this next couple of examples are about. So we got some definitions here. A demand function. Demand is the relation between the price of an item and the number of that item that we sell. Okay. Revenue function. Revenue is a relation showing the amount of money taken in based on the number of items sold. So obviously, the more you sell, then the more your money you're going to take in. So we have an equation that we can use to help us work that out. If we know that the demand function for a product is P at X, as you can see defined up above, then X times P at X will give us the revenue. So we can use this demand function to create a revenue function, and then it's going to be a quadratic, and we can find the maximum revenue. Going back to this graph here, the maximum revenue would occur at the vertex, and then we could, from that, decide what the best price, the best amount of a product to create is in order to get the maximum revenue for our business. That's what this particular type of word problem is going to be getting at. So here's an example. The demand function for a product is given as P at X equals negative 2X plus 5. And this is pre-filled in for us just to save a little bit of time. So determine the revenue function. So X times P at X. Okay, so that's just from above. So the revenue function based on this particular demand function would be X times negative 2X plus 5. If I do distributive law here, then I'm going to get negative 2X squared plus 5X. And this would be my revenue function here, and it's a quadratic, right? If I want to find the maximum revenue that I can get, I want to find the vertex. The easiest way to get the vertex, if you get good at completing the square, is to do that, to complete the square. So we've already done a bunch of examples above, so this is filled in for us, but remember we're going to common factor out this negative 2 from these two first terms are going to common factor out the negative 2. So negative 2x squared divided by negative 2 gives x squared. 5x divided by negative 2 gives me negative 2.5x. Then we take half of that negative 2.5x and square that. That gives us the 1.5625, which we add and subtract. As we know, it's only the first 3 terms that we want for our perfect square, which means that I want to take this negative number outside the brackets. But to do it, remember I have to multiply it by this number that's out front, the negative 2, and that's where negative 2 times negative 1.5625, that's what gives us the 3.125. And then I can take half of this middle number, this negative 2.5, that's where negative 1.25 comes from, and there's my perfect square, and put it all together. There's the equation in vertex form. And so the vertex is going to be um, 1.25 and 3.125. So the maximum revenue, remember revenue is measured on the y-axis, the maximum revenue is going to be the y value, which is the 3.125 that is already boxed here, but I'll put another box around it. So the maximum revenue is around $3.13. So we can get a maximum revenue just by completing the square once we have a quadratic revenue function. We can also talk about things like cost and profit. Cost, as I'm sure you can figure out, is simply the cost of an item based on the number of that item sold. Obviously, there's a certain cost for producing items. And the profit is just the difference between revenue and cost. So revenue is how much money I take in. Cost is how much money it costs to produce a product. The profit's the difference, right? So profit function is just revenue minus cost. And the last definition, break-even points, that's the point at which profits equal 0. So in other words, if you break even on a, let's see, just draw a little graph here. If this represents my profits, now I've got profit here and versus x, then the x-intercepts would be where I'm getting 0 profit. I'm not losing money. That would be below the x-axis, but I'm not making money either. So break-even points are the zeros of the graph. So a revenue function for a product is given as negative 2x squared plus 24x. The cost function is given as 8x plus 15. So determine the profit function. Again, this one's done for us to save a little time because I know this is a longer lesson. You might even want to break it up a little bit and come back to it. But assuming you're still with me, we know that the profit is revenue minus cost. Let's use a different color here. So let's do cost in green. So profit is going to be the revenue minus the cost function, right? So cost was 8x plus 15. Revenue was negative 2x squared plus 24x. We're subtracting them, which means that when I subtract this second bracket, the signs are going to change to a negative 8x minus 15. When I collect my like terms, I just got a new function that's a quadratic, negative 2x squared plus 16x minus 15. If I want to determine the value of x that's going to maximize profits, that's actually still looking for the vertex, but it's looking for the x value of the vertex. So here are the steps. I won't read them over again because we've done a whole bunch of completing the square, but if you look through that, you'll see those are the steps for completing the square. When you get down to the bottom, that is the final product in vertex form. The vertex is 417. And so again, it's looking for the value of x that's going to maximize the profits. So that would be the x value of the vertex. So the value of x that maximizes the profits is 4. So whatever x stands for, so 4 products sold or 400 or 4,000, that's going to maximize profits. Now the break-even quantities, as I showed above, are the zeros. So we have to find out where the x-intercepts are. If we've got something in vertex form, like we just got in the previous part, in part B, an easy way to get the zeros is just to set y equal to 0, because whenever we set y equal to 0, we're going to find the x-intercepts. So we're going to set, in this case, p at x is our y value. So we're going to set that equal to 0. And then we're just going to go about isolating x, which we can actually do pretty easily in vertex form because the x only shows up once. So all we have to do is do opposite operations in the opposite order, and we will get x by itself. So first I'm going to subtract 17 from both sides. Then I'm going to divide both sides by negative 2. Then I'm going to take the square root of each side to get rid of this squared here. And then I'm going to add 4 to each side. When I took the square root, I just need to point out that when I took the square root, we got a positive and a negative answer. Because in order to get 8.5, this 8.5 that's under the square root sign, I could square a positive number or a negative number to get 8.5. Think of it this way. Say instead of being 8.5, I wanted the square root of 9. Well, I could say that's 3, but it could also be negative 3, couldn't it? Because negative 3 squared, if I'm just doing the opposite, would get me back to 9. So there's actually two answers, positive or negative of the square root, which is 2.9 in this case. So if I take positive 2.9 and add 4, like in the last step, I get 6.92. But if I take the negative 2.9 and add 4, then I get 1.08. So I've got two different answers here. So this last part of this lesson was taking what we know about completing the square and using it on different quadratics, mostly to help us find the vertex, although in the last question we also used it to help us find the zeros. So that was a very long lesson, I know, and again you might need to go back and review some of it, but it's definitely stuff that you need to understand in order to work intelligently with quadratic functions. So once you've got your energy and your enthusiasm back, I need you to do these questions here at the bottom.